Let's take a look at the case where we have a rigid body rotating about a fixed axis. Well, the object itself consists of multiple particles, so we're going to take a look at the force and ultimately the torque on each particle individually. And so we'll start with F equals ma. And this is the tangential acceleration, looking at it linear. Well, to get the torque, we know it's the radius times the force, so RF. And what we do on one side, we need to do to the other, so MA times that radius. So now the left-hand side is the torque, R times F is the torque. And over here, M, remember our definition, the linear or tangential acceleration is related to the angular acceleration by that factor of R. So our angular acceleration times R is the same thing as the linear acceleration. So we're going to substitute that in for A, and then we still have times R over here on the side. And then lastly, just a little bit of simplification. So tau equals mr squared alpha. Okay, and so that's for each individual particle. And since it is a rigid body, that means that all the particles are moving together. So that means each particle has the same angular acceleration. So the net torque for the whole object is going to be the sum of this mr squared times alpha. Same angular acceleration for every particle, and we are summing this up over every single particle encompassed in this body. Well, this summation term has a special name. This sum of mr squared is our rotational inertia, and we're going to symbolize this with the capital letter I. So I is rotational inertia. And so now we have a rotational form of Newton's second law. Net torque equals I alpha. And so inertia, we're going to define that. It's the, if y'all recall, it's the tendency for objects to resist changes in their velocity. And rotational inertia is the tendency for objects to resist changes in their angular velocity. And so we can think of I as the rotational form of mass, almost. All right, and that is what we will be talking about in today's topic.